communicate securely, you need a shared secret key. But to share that key safely across an open network, you already need secure communication. This circular logic created a logistical wall that cryptography could not scale for centuries. Here we look at the final entry in the cryptography and data category, algorithm number 50, the Diffie-Hellman key exchange. It bypasses this problem entirely, allowing two parties to build a shared secret in plain sight. Before 1976, military and digital security relied entirely on physically transporting a key beforehand. You had to hand someone a briefcase or a codebook, creating a massive logistical bottleneck. Then Whitfield Diffie and Martin Hellman published a paper titled New Directions in Cryptography. They realized the goal shouldn't be finding a secure way to deliver a key. The goal was to let anyone listen in on the delivery, but make the intercepted data mathematically useless. By eliminating the physical exchange of keys, they laid the foundation for secure, spontaneous, global communication. This concept makes the modern internet possible. To understand how two people can agree on a secret while shouting across a crowded room, we can use a physical analogy: mixing paint. Mixing two colors together is incredibly easy, but unmixing them back into their original components is virtually impossible. This diagram illustrates the paint mixing intuition. Alice and Bob publicly agree on a common base color that anyone can see. Next, each person privately selects their own secret color and stirs it into the public base paint. They swap their mixed cans openly. Eavesdropper Eve intercepts them, but cannot unmix them to deduce the secrets. Finally, Alice and Bob stir their own secret color into the received can, arriving at the exact same shared blend. In computing, this mixing represents a process called modular exponentiation. The unmixing represents the discrete logarithm problem. The safety of your data relies on the math being extremely fast in one direction and practically impossible to reverse. Looking at the mathematical mechanics in this diagram, we replace the public paint with two public numbers, a large prime, like 23, and a generator, like 5, agreed upon in the open. Alice picks a secret number, 6. She raises the generator 5 to her 6 modulo 23, resulting in 8. Bob does parallel math. He picks secret 15, calculates 5 to the 15th modulo 23, giving a public value of 19. They swap their public numbers, 8 and 19, across the open channel. Alice raises Bob's 19 to her secret 6. Bob raises Alice's 8 to his secret 15. Both calculations perfectly arrive at the exact same shared secret, 2. This chart contrasts the difference in effort, showing how the eavesdropper is trapped by computational asymmetry. To steal the secret from the public numbers, Eve must calculate the discrete logarithm to reverse engineer the original exponents. This mathematical trapdoor secures the exchange, but it has one specific flaw. Because these numbers don't verify identity, Diffie-Hellman requires secondary authentication, like digital certificates, to prevent man-in-the-middle attacks. The forward calculation is highly efficient. By using square and multiply exponentiation, computers execute this in big O of log A time, processing massive 2048-bit numbers in microseconds. Conversely, the best classical method to solve the discrete logarithm, the general number field sieve, runs in sub-exponential time. It would take modern computers millions of years to break a strong key. This security gap is vulnerable to the future. A sufficiently large quantum computer running Shor's algorithm can solve discrete logarithms in polynomial time, collapsing the defense entirely. For now, the implementation remains incredibly elegant. In Python, the built-in POW function handles the entire complex math, taking the base, exponent, and modulus to instantly calculate the shared secret. A complexity gap that separates a microsecond calculation from a million-year brute force search is collapsed into just a few lines of code. Diffie-Hellman acts as the invisible handshake behind modern secure communication, establishing the keys for HTTPS, SSH connections, virtual private networks, and messaging protocols like Signal. Today's standard uses ephemeral keys, or ECDH. By generating a temporary key for every single session, it guarantees forward secrecy. Even if a server is breached years later, past communications remain locked. This brings us to the end of our dive into the underlying architecture of software, exploring the source repository from Imran Ahmed's book, 50 Algorithms Every Programmer Should Know. Our thanks to the author and Pact Publishing for outlining the definitive toolkit of computer science. From the first sort to the final hash, these 50 algorithms demonstrate the same principle, that the right mathematical structure can reduce a billion-year computational hurdle into a manageable, everyday operation.